Right, question 2 was about comparing the Kekulé's model of benzene and the delocalized model of benzene. So they want you to describe that, but also with the aid of suitable diagrams showing the orbital overlap. Okay, and then describe the difference between structure A and structure B. Now, using Kekulé's ideas, these were 3 separate alkenes. Okay, so the way you form alkenes is going to go back to F322 last year. You're going to show the p orbitals and then sideways overlap. So let's say that was one of the alkenes. There's the pi bond. We've got 3 alkenes in structure A. So there's my second and third pi bond. You also want to, of course, label the p orbitals and mention the words sideways overlap. Draw my benzene at slightly different orientation to what it has up there. Same thing. Right, of course, with the structure B, you've got that delocalized ring. Once again, the p orbitals overlap sideways. You get 2 delocalized rings, one above and one below. Okay, and that's the delocalized model. Right, so that was a diagram. Let's now describe it. So there's 1 mark for the diagrams. They only want the final pictures, not the initial. Right, and then in structure A, of course the p orbitals overlap sideways to form the pi bonds, but they are localized. The pi electrons are localized between 2 carbon atoms. Okay, 1 mark there, second mark. Right, structure B, once again the p orbitals overlap sideways to form once again pi bonds. However, this time the pi bonds, instead of pi electrons, are delocalized. Well, it was one extra mark for saying p orbitals overlap sideways, which you've got 3 times here. And the word delocalized had to be spelled correctly. Right, so they give you, again, referring back to the last question, so C6H6, which is benzene, again, there's 2 different representations, the Kekulé model and the delocalized model. And they've also talking about C6H10, so with 4 extra H's, it's basically a cyclohexene. Right, so when you hydrogenate cyclohexene, enthalpy change is minus 119 kilojoules per mole. So if the actual representation of benzene was the Kekulé model, you would expect enthalpy change to be 3 times minus 119, which gives you minus 357. Right, but for actual benzene, it's not 357, it's minus 208. Okay, so that must mean it's not the Kekulé model, but something more stable. That's the delocalized model. Okay, so that was B. Structure B. So structure B is a better representation of benzene, and to get the first mark you also have to say why, because the enthalpy change of hydrogenation is less exothermic, it's minus 208, than the expected minus 357, which comes from 3 times minus 119. Okay, that was the first mark. Okay, so structure B is actually more stable, we could say lower in energy, by 149 kilojoules per mole. That's the difference between 357, the expected, and 208, the observed value. Right, part B, we've just tested your understanding of curly arrows. So from step 1, in step 1, and then what they want to do is add curly arrows to the diagram, and what's changed is that you've broken this CN bond. Okay, and if you look at the products, the positive charge has gone on the end, so it must have gained 1 more electron that it did not have initially. In that bond, you've got 1 electron from this N atom, 1 electron from that carbon atom. The N atom has gained 1 more electron. That must mean that when this bond broke, both electrons went to that same nitrogen atom. It was heterolytic fission. Okay, so the bond breaks, of course this carbon's losing out on 1 electron, which is why it's got a positive charge. So it's a bit like the curly arrow mechanism for alkenes, addition of bromine to an alkene, we formed Br+, going back to F322. Right, and then what happens is the positive and negative attract, but of course the arrow starts from the lone pair, goes straight towards that carbon atom, so you're making a new carbon-fluorine bond. 1 mark for each of those curly arrows. Right, application here. So you know that you use FeBr3 when you are doing substitution reactions with benzene and bromine. Okay, so that helps to make the more the more reactive electrophiles, Br+. And the way it does it is by pulling off a bromine from Br2, so form FeBr4- and also a Br+ electrophile. Now this more powerful electrophile can then react with the benzene ring. So what's happened here is all they've done is replace the first bromine in Br2 with this extra group. Okay, it's alkyl group. And now if you add in FeBr3, there's only one bromine it can pull off to form FeBr4-, and that means there's going to now be a positive charge on this part of the molecule which the benzene ring can then react with, and you see it now attached onto the benzene ring. Substitution reaction, H falls off, you're going to make HBr. And they want the equation, so similar to what you met with benzene. So you'd have FeBr3 plus, not Br2, but CH3 twice CHBr. FeBr3 is going to pull off the bromine, going to form FeBr4- and CH3 twice CH+. Because I've put a circle around it. Now you know the positive charge is going to be on the carbon because you've broken a carbon-bromine bond. Carbon has now got one less bond. Okay, and of course then the benzene is going to react with that electrophile. It's now end up on the benzene ring via a substitution reaction. Right, you're going to make compound D. You've got an amine on a benzene ring, or two amines. So it's an aromatic amine, and you're going on to N2+, because that's if you dry out fully. There's your benzene ring. It's going to be N triple bond N. That N's got 4 bonds, not 3. It's got a positive charge. You know, if you use HCl to make the diazonium salt, you can have a Cl- there as well. Right, so the way you do that, they wanted the reactants. Okay, so you use HNO2 and HCl. They only wanted the HNO2 for the mark, or could even have said NaNO2 and HCl. That's how you make the HNO2 in the first place. Okay, we'll mark there. Right, this was the tricky bit. So going back to the last question, well, what you've done here is you've attached on this extra alkyl group with also an NH2 on the end. And another giveaway was FeBr3. Okay, and what FeBr3 does, once again, it's pulled off a bromine atom and you're going to be left with a positive charge, and the benzene ring is going to, of course, be attracted towards that positive charge. So these are the new bonds that you've made. Okay, so initially what you must have had was that. Okay, and of course you only make these bonds by there being a positive charge, but like how the benzene ring attracts a Br+. Okay, so but to make that positive charge there initially you must have had a bromine. Okay, so the FeBr3 pulls off the bromines, get a positive charge, and then the benzene ring is attracted towards that positive charge on the carbon, and you make new carbon-carbon bonds here. Okay, but once again the giveaway was the FeBr3. What it's going to do is pull off the bromine atoms, and then that must have been the rest of the molecule. That was also linked back to the last question where I showed you how it was done. Where you do have Br2, but bromine on a carbon atom and an alkyl group. And then the difference between this compound and compound D is you've got this extra bit over here. Right, and what we've done here is make an amine bond. You can make an amine bond by an amine reacting with a carboxylic acid. So that there must have been a carboxylic acid initially. So just redraw this molecule up here, but with the OH for the carboxylic acid. So the acid plus the amine group join together in a condensation reaction. Water is eliminated, and you make your amide bond. Right, so going back to that flow chart on the last page, this is the compound you started with. They eventually ended up with compound D. They're all 1-to-1 ratios in the equations. Okay, so by a few steps you made compound D. Right, they've told you now what the percentage yield was. Okay, and they've also told you the molecular mass of compound D. And they want you to work backwards to work out the mass of 1,3-diaminobenzene needed or required to make a 40% yield of compound D. Right, 1.73 grams of compound D was prepared, so you can work out how many moles that was of compound D, 1-to-1 ratios throughout that flow chart on the last page, therefore you can work backwards, but that's only 40% though of moles. You're going to have to scale up to work out 100% of moles and therefore and then convert it into a mass in grams. Okay, so first of all, I worked out the moles compound D that I made. Again, that was only 40%, so when I'm working backwards to work out moles of 1,3-diaminobenzene, which I can then turn into a mass in grams, I'm going to have to scale up. So that's only 40% of the moles. I'm going to do 100 over 40 for the scale up, times 0.005. So 0.0125 moles is what I would expect to have got if I had 100% yield, and also that would have been the same number of moles of 1,3-diaminobenzene. Right, how many grams? Because when I work out the mass of the starting material used. Okay, right, so we want to work out the mass in grams. It's going to have to be moles, which is 0.0125 times the molar mass, which work out is 108, and you get 1.35 grams. Okay, so when you compound D has been developed for possible use as a drug to treat heart conditions, and when it's going to patients, only 25% of the dose is effective. Now, you know, if you've got a chiral carbon atom, you're going to form two optical isomers, only one's going to be effective, so only 50% of the dose will be effective. So if 25% of the dose is effective, that must mean you had 2 chiral centres. If I go back to compound D, okay, so here's one chiral centre where you got 1, 2, 3, and what you can't see is the H, because it's skeletal, so there's one chiral centre, one chiral carbon. Here's the second one. Now, if you only had one chiral carbon atom, that would give you 2 optical isomers, 50% is effective. If you had 2 chiral centres, or 2 chiral carbon atoms, 2 optical isomers plus another 2 optical isomers, 4 possible optical isomers, only one would be effective, 1 out of 4 is 25%. Okay, so why is only 25% of the dose effective? Because compound D has 2 chiral centres, one mark, therefore 4 optical isomers exist, mark 2. How could you make the dose more effective? Well, just use that one optical isomer that is effective. Okay, and you can make that, so make your dose more effective by synthesizing just that one desired optical isomer. You do that by, okay, you can use, for example, biological catalysts such as enzymes, or a chiral transition metal complex, or a chiral pool. So just one of those answers for the third marking point.